All right, so now we want to do problem 1 from chapter 7. Problem 1 says, so the problem says a proton that has a mass that's 1.67 times 10 to negative 27 kilogram is being accelerated along a straight line at 3.6 times 10 to the 15 meter per second square in a machine. So this is your acceleration. You're given the mass. If the proton has initial speed that is 2.4 times 10 to the 7 meter per second and travels a distance of 3.5 centimeters. What is the speed and the increase in its kinetic energy? All right. So you're given the acceleration, you're given initial, you're given the distance, so it becomes quite straightforward to calculate the final velocity because because one of the equations that has all the information that we would need, and that equation is the final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the horizontal distance or the displacement. So we have everything what we have in front of us. So initial velocity is this 2.4 times 10 to the 7. You square it, and then plus 2 times the acceleration. The acceleration is 3.6 times 10 to the 15, and then times the displacement. The displacement is 3.5 centimeters. So 3.5 times 10 to the negative 2 meters, converted to SI unit. So we have this. So after you punch in the calculator, the final velocity or the speed, you should have 2.87 times 10 to the 7 meter per second. Okay, so you have the final velocity, and that is calculated using the equations of motion, and you have initial velocity, and then the problem says that, and you're asked to find the increase in its kinetic energy. Because it's being accelerated, so we know that the final velocity has to be greater than the initial velocity. And with that, what does it mean? It means that when they acquire the final velocity, it will have a higher kinetic energy. So the question is, what is the change in kinetic energy? To find the kinetic energy, of course, we can calculate the initial kinetic energy, and we can calculate the final kinetic energy and find the difference. That gives you, the difference of the change in kinetic energy. If it's greater than 0, of course, that means that it has increase in kinetic energy. Okay, so what is the expression for calculating the kinetic energy? That would be just 1/2 mass times v squared. So it's 1/2. And the mass is 1.67 times 10 to the negative 27, and then v squared. So your v is 2.4 times 10 to the 7. You square it, so that your initial kinetic energy should have a magnitude of 4.81 times 10 to the negative 13 joules. What about the final kinetic energy? Your final kinetic energy, you still use 1/2 mv squared. So I'm just going to write down m and then vf squared. After you plug in the numbers, your VF, of course, is that equation. You should get 6.87 and then times 10 to the negative 13 joules. Okay? So you have this amount of energy initially, and then after it's being accelerated, it acquires, it has attained the kinetic energy of that value. So the change in kinetic energy, of course, is always the final kinetic energy minus initial kinetic energy. So you have this minus that. That should give you 2.06 times 10 to the negative 13 joules. Okay, so this is a simple problem that is very straightforward. You're given the velocity, you're asked to find the kinetic energy, and the object is being accelerated, so you can use that information to calculate the final velocity and then find out what is the change in kinetic energy. Okay, so next one we want to do is problem 13. Alright, a luge and his rider with a total mass of 85 kilograms emerged from a downhill track onto a horizontal straight track with an initial speed of 37 meter per second. So the mass is given, the combined mass is 85 kilograms, and the initial speed is 37 meter per second. If a force slows down to a stop at a constant rate of 2 meters per second, what does that mean? Slow it down. So your A, if you look at the units, that is your A. So it's -2. Why is it negative? Because it says that it slows it down. So you have to manually put a negative sign in front of it. What magnitude of force is required for the force? So you want to find the force magnitude to slow it down, and what distance it travel while slowing. So the distance, let's say x, okay, and how much work is done by the force. So I want to find the work done by the applied force, and then so let's do this first, okay. All right, so how do we calculate the force? So the whole thing, this one is like moving. It's being slowed down by applied force with the acceleration that's given. So the force acting on the system would just be the mass times the acceleration. So how do we calculate force magnitude? So we can just use ma, F equals ma, straightforward. So you have mass, that's 85, and the magnitude. So you have let's see if we want to keep the negative. So you have the acceleration is -2. So you should have a force that is -170 Newton. Okay. So on the inside simply indicate the direction as well. Okay. Now, so how much distance that it would have traveled before it comes to a complete stop? What does that mean? When it comes to a complete stop, it means that the final velocity is 0. So you have the initial velocity, you have the final velocity, you have the acceleration. So to calculate the displacement now becomes straightforward. So you will have, let me just write here, so you have the Vf squared, that's equal to Vi squared plus 2a times delta x. No final velocity becomes to a stop, and the initial velocity is 37, so you square it. And then plus 2 times your acceleration is -2, and then delta x. That's your total displacement. So once you calculate this, your delta x, you should have a magnitude that gives you 342.25, and that's in meters. Okay. So this is the amount of displacement that the sledge has moved. And then you're asked to find how much work that is done by this applied force. Okay, so how do we find the work? What is the definition of work? The definition of work is force times displacement, right? So and also how they what is the direction of force and what is the directions of the displacement also plays a role, because this is the scalar product. So that will be force magnitude. When I say magnitude, it means that just use the absolute value of that quantity, and then times the displacement magnitude, and then times cosine of the angle between them. Okay, so if we look at this, so the diagram will be something like this. So you have the sled that's coming down, and then with initial velocity. So that's if it's moving this way, okay, or if you want to. Let's say it's moving, so it slides down, and the whole thing, this is moving, so this is your 0 meters, and then this is the 342.25. So this is moving in this direction. So this is the directions of displacement. Now the force, however, is trying to trying to slow it down. So the force is in this direction. Okay, so you can see that they differ by 180 degrees, phase difference. So when you do this, you have the force magnitude times times delta x, and then there's a minus sign in front of it because they are opposite of each other. So it's 180 degrees. Or if you want to just write it in terms of the angle, so you have F delta x and then cosine of 180 degrees. Okay. So force is 170. Like I said, you want to just use the magnitude, and then 342.25, and then times cosine 180. So you should get a value. The work done by the force is simply equal to negative, because you have a phase difference. Negative, let's see, 5A1A2.5 joules. So this is the amount of work that's done by the applied force acting on object, and you can see that it is negative. What does that mean? When you have a work that's negative, remember, work is what is the force to to transfer energy. So if the applied force does negative work, it means that it lowered the energy of the system. So the energy, so that's why it begins with the initial velocity, and then after some time it comes to a stop because this work acts to transfer the energy out of the system. Okay, so it's negative. Okay. All right. So let's see. And then the problem, says that if the acceleration is slow at 4 meters per second squared, what will all this quantity be? Okay. So in other words, if this is -4, what would that be? So let's see. So that everything stays, all the formula stays the same, doesn't change the equation. But then the magnitude-wise, let's see what do we get here. So the force is basically doubled. What about the displacement? So initially you have 37 meters per second. The acceleration now becomes -4. So let's see what the displacement is. So the displacement, after you punch into a calculator, the displacement is 171.125 meters. So you can see that when the acceleration increases, the displacement actually decreases. And that makes sense because when you have a larger acceleration, then you don't need that longer distance to get to the final results. So with the larger acceleration, you can shorten the distance. Okay. Now, what about the amount of work? So the answer here is 171.125. So what is the amount of work that's done, by this force when combined with this acceleration and with that distance? So we can just use this formula, F dot D. It doesn't change. The symbol does not change. But now the numerical value, let's see what's changed. So force now becomes 340, and the displacement is 171.125. They're still, opposing in the opposite direction. So after you did the calculation, you still get this amount of work. Okay. Why is that? Because work basically, is equal to force times displacement. So if the force increases, it just means that displacement decreases, and then so the net work is actually the net work doesn't change. The other thing is that if you remember the work kinetic energy theorem, so work is equal to the change in kinetic energy. You start out with the same initial velocity, you ended up with the same final velocity. So the amount of energy, the change in kinetic energy does not change, right? Delta K does not change. So that's why your work does not change as well. Just that so within this intermediate state, you can see that when one thing changes, the other thing will change as well. But the combined result does not affect the whole thing. Your W is still equal to delta K. And when the velocity doesn't change, the initial and the final do not change, then it does not affect the amount of work done by the force. Okay, so that's basically what this problem illustrates. And the next one we're going to do is problem 15. All right, problem 15. So let me draw the diagrams. All right, so this diagram shows three forces applied to a tron that moves leftward so it's moving leftward by 3 meters over a frictionless floor. So the displacement, it says, is 3 meters, and it's leftward, okay? And the force magnitude are F1. F1 has 5 Newton. So in unit vector notation, we will say that it's negative I hat because it's pointing leftward. And then F2 has 9 Newton. So this is 9 Newton. And I'm not going to give a direction because it has both X and Y components. So let's just say the force magnitude has 9 Newton. And the F3 has 3 Newton. So F3 is pointing downward. So in Newton vector notation, that's -3 and then J hat Newton. Okay? And the angle is 60 degrees. So this is 60. So during the displacement, what is the net work done on the trunk by the 3 forces, and does kinetic energy of the trunk increase or decrease? So you want to find the net work done by these 3 forces. There are 2 ways of doing that. And one is that you find out, so your net work can be found as when the work done by F1 plus the net work done F2 plus the net work done plus the work done by F3. Or this is equal to the, so individually, so what is this? This will be the F1 dot D, and then this is your F2 dot D, and then this is your F3 dot D, and then you just add them together, right? Or you can just say that net work is basically equal to net work scalar product, the displacement, the net displacement. Okay. So let's do the individual one first, and then I'm going to show you the easiest one. Okay, so net work is the work done by F1, F2, F3. So let's see what is the work done by F1. The work done by F1, this is the force that's -5, and the displacement is also is -3. So when you do the net work, that because they're in the same direction, so we can have the force magnitude times the displacement times cosine of 0 because they are in the same direction. So you will have 5, and then times 3, and then times cosine of 0, and that gives you 15 joules. So this is the work done by F1. Let's see, what is the work done by F2? The work done by F2, you can see that F2 is pointing in that direction. So it has 2 force components. One is here, and one is there. Now let's look at this. We have the the force magnitude has 2 components: the horizontal component and the vertical component. The horizontal component is in the directions of the displacement, but pointing in the opposite direction. And the vertical component, it is perpendicular to the displacement. When you have something that's perpendicular to the displacement, that does not contribute to work, because when you do a scalar product, the force here, the component, that will be 9 times sine of 60 degrees, and then times the displacement, and then times the cosine of the angle between that. The angle between them is 90, so that does not contribute. Now, what about this one? So the S component has 60. I'm sorry. The S component has the magnitude of 9. So you have 9 times cosine 60 because it's adjacent. So this is the force magnitude. The displacement is 3. But then they are differ by 180 degrees. So when you do this calculation, the work done by the second force is equal to -13.5 joules. Okay? And this component does not contribute to work because the angle between force and magnitude is 90. What about F3? The work done by F3, using the same argument, F3 is in this direction, and its displacement is in that direction, which means that they are differ by 90 degrees. So when you do that, whatever F3, so you can have F3, and then times displacement, and then times cosine of the angle between them. So that just gives you 0. So then when you add add all this together, that gives you the net work, because you don't have any other forces. You don't have any other forces, in the horizontal direction. So in fact, you also have the gravitational force as well, and also the normal force. But then because they're all in the vertical direction, so that basically they don't count. Okay. So after you add up all this, you get 1.5 joules. The only thing that is important, the only force component that is important is along the directions of the horizontal of the displacement. So displacement is horizontally, so which means that all the forces in the vertical do not contribute. Okay, so this is how you do that. Or you can just use, so add up all the forces, and then you find out that's 1.5. Or you can just find the net force in the same direction as the displacement. So the net force, if you look at this diagram, like I said, all the vertical components do not count, so you only need to consider this force and this force. So this force has magnitude of 5. And this force, horizontally, this force has, do I have here? Let me see. This force have 2 times cosine. This force has the have 2 and then times cosine 60. Okay, so the difference. So the net force will just be F2 cosine 60 and then minus 5, right? So this is rightward and this is leftward. So that's your net force in the horizontal direction. So the net work will just be net force in the horizontal direction times the displacement. That is your 3. Okay, so whatever value that you have, and then and then times that gives you so this will give you, so I did calculate the net force in the horizontal direction. So this gives you negative 0.5 Newton. Okay, so when you apply this, you will have 0.5 again. I'm just using the magnitude times the displacement and then times the angle between them. The angle between them, because we assume that it is rightward, so they differ by 180 degrees. So, wait. Let's see. So you have net force, which is negative. Okay, so if we keep this negative 0.5 and then times negative 0.5, which means that the net force, this is the direction of the net force. Okay, let's put it that way. So the net, because you got a negative sign here, so the net force is leftward, and the displacement is also leftward. So you have the 0.5, we just use the magnitude 0.5, and then times 3, and then times cosine of the 0 degrees between them. So you got 1.5 joules. Okay, so once you find out the net force, and then see which direction it is pointing. If it's in the same directions of the displacement, then it can produce the positive work. If it is pointing in the opposite directions of the displacement, then it produces a negative work. Okay, so basically that is that, and and then the question also asks, whether the kinetic energy increases or decreases. Because we calculate net work that is greater than 0. What it means is that delta K, if you remember what kinetic energy, delta K is equal to W net. If this is greater than 0, which means that the final kinetic energy is greater than the initial kinetic energy. Okay, so that is that. Okay. All right. So the next one we want to look at is problem 17. Let's see what problem 17 is. A helicopter lifts a 72-kilogram astronaut 15 meters vertically from the ocean by means of a cable. Okay, so diagram. So you have a helicopter that draws. So this is the astronaut, and there's a cable that's taking the astronaut off the ocean, and it's moving vertically from this point to that point to the helicopter. That's 15 meters. Okay. And then this the weight is the mass is 72 kilogram, and the acceleration of the astronaut. So there's a acceleration of the astronaut. So that is 1/10 of a g. And how much work is done on the astronaut by the force from the helicopter and the gravitational force on her just before she reached the helicopter. Okay, and what are the kinetic energy and the speed? All right, so you have a cable that is tied to the astronaut, and you have the helicopter trying to pull the astronaut off the ocean, and the distance between the astronaut and the helicopter is 15 meters. So the whole thing is moving upwards, and because the helicopter is providing a force moving upwards, so the astronaut has the acceleration that's tenth of a g, and the weight is 72. So just by looking at this diagram, we know that we can draw a free body diagram. So this is the weight of the astronaut, and this is the cable that's connecting to and moving upward, and the whole thing is moving upward, which means that the tension is greater than the gravitational force, and in such a way that there is a non-zero acceleration. So we can actually calculate what is the force magnitude of that tension, and that tension of the cable is basically coming from the helicopter. So once you find out the force magnitude, then you can use that to calculate work because the displacement is given. Okay, so we can say T minus mg has to be equal to ma. So you can calculate your T. T would just be ma plus mg, and all these informations are given. So you can calculate the magnitude, which is 776.16 Newton. So this is the amount of tension from the helicopter. Okay, so how much work is done by tension? Of course, that will be just F dot D, or tension, whatever tension that you have. So tension has 776.16. Displacement is 15. They're both in the same direction, so it does positively work, which means that the kinetic energy has to be greater than, has to be increased. So what is the amount of work done by the tension? That will be 11642.4 joules. This is the work done by tension. Now, let's not forget that there's a gravitational force downward. That's downward. That can also does work on the astronaut. So we need to figure out how much work that is done by gravitational force before we can attempt to find the net work done by the combined force. Okay. So what is the work done by gravity? The work done by gravity would just be gravitational force times displacement, right? Gravitational force is downward. Displacement is upward, so they differ by 180 degrees. So you can just use the magnitude, which is 72 times 9.8. That's the force magnitude. Displacement is 15, and we already know that they're pointing in the opposite direction, so we can just put negative sign in front of it instead of just using cosine of 180 degrees. So your WG, after you do the calculation, you should get negative 10.584 joules. Okay, so what is the change in kinetic energy? So we have this work done by the table, work done by the gravitational force. So the net work would just be the sum. So you have WT plus WFG. So after you add those two together, you will get 1058.4 joules. Okay, and what does that mean? That means that this is the change in kinetic energy. So net work is equal to delta K. So you have your Kf minus Ki, right? And let's say initially the astronaut is not moving, so it has zero kinetic energy. So this term goes away because there's no velocity. So which means that the final kinetic energy should have the value of 1058.4 joules. So this is the amount of energy that goes into the astronaut after it's being pulled to the helicopter. And then you're asked to find what is that velocity then. If the initial velocity is 0, the final velocity, what would that be? You already calculate the final velocity, the final kinetic energy to be this magnitude. So just set it equal to 1/2 mv squared. You have the mass, you have, so you can just quickly calculate the VF. So your VF, after you plug in the numbers, your VF would just be, let's say, you can do that. So your VF would just be 5.4 meter per second. Okay, so you can do that, or if you want to use the equations of motion, which is Vf squared is equal to Vi squared plus 2a times delta x, you can do that too, because this is 0, and your A is given 1/10 of g, and delta x is, or delta y is 15. So you can plug into this equation to calculate your final velocity, or you can just use this more direct forward. That's more straightforward. That the final kinetic energy is just equal to the 1/2 mv squared to find your final kinetic energy. To find the final velocity. Okay, so that's that.